Screen visible இருக்குங்களா? Anyone?
Yes, sir.
Yes. Okay. So இதெல்லாமே previous year gate questions தான். Based on random process. நம்ம random process last class முன்னாடி கிளாஸ்ல பார்த்தோம். ஸோ அதை பேஸ் பண்ணி நம்ம கொஸ்டின்ஸ் இந்த இப்போ ப்ரீவியஸ் இயர் கேட் கொஸ்டின்ஸ் இதெல்லாம் வந்து சால்வ் பண்ணுறோம். ஸோ ஃபர்ஸ்ட் ஆஃப் ஆல் ஜென்ரலாகவே கேட் ஆர் எனி அதர் எக்ஸாம் ஒன்ஸ் அந்த கொஸ்டின் பார்க்கும்போது பார்த்த உடனே இது நம்மளுக்கு தெரியாது அப்படின்ற ஒரு முடிவுக்கு வந்துடக்கூடாது. ஜஸ்ட் உங்களுக்கு பேசிக் தெரிஞ்சதை வச்சு ட்ரை பண்ணணும். ஓகே, இப்போ என்ன கொடுத்துருக்காங்கன்னு பார்ப்போம். தேவ் கிவன் சம் ரேண்டம் ப்ராசஸ் எக்ஸ் ஆஃப் டி, தட் இஸ் 3v of t minus 8. Again, v of t is also a random process. If v of t is random, then x of t is also random. And then they mentioned v of t is having zero mean. Zero mean. That means I know what is the characteristics of v of t. So the expectation value of v of t is 0. V of t is 0. Then they also mentioned autocorrelation function for v. Autocorrelation function for v, that is 4e power minus 5 mod tau. Now they are asking what is the power in x of t. First of all, you should know what is the power formula in the random process. For random signal, power is simply e expectation of x square of t. This is the power of the random signal, power of the random process. So they mentioned x of t is equal to 3 times of v of t minus 8. So again, we have to do the square operation. Okay, whatever the signal given x of t, that we have to do the square. So we'll get 9v square of t minus 48 v of t, then plus 64. Then you apply the expectation operator. Okay, the constant can be taken out, you know that. So expectation of e of v square of t, then minus 48 v of t, and then 64. So now to get the final answer, you should know what is expectation of v square of t, then what is expectation. Again, we have to apply the expectation operator inside. Sorry, here we made a mistake. We have to apply the expectation operator inside. So 9 times e of v square of t, then minus 48 e of v of t, then you know that expectation of constant is always constant, so that is 64. Now what is e of v square of t? So e of v square of t means power in the signal v of t. Okay, but that is not given directly. Okay, so they given autocorrelation function. They given autocorrelation function. So from that you have to calculate the power. From that you have to calculate the power. You know, autocorrelation at origin will give power of that particular signal. The moment I put tau is equal to 0, I'll get 4. So 4 watt is the power in the signal v of t, because autocorrelation at origin will give the power of the signal. So this is 9 into 4. Why I am calculating the power? Because expectation of v square of t, that means power. Then what is expectation of v of t? That means mean value. So they given already mean is 0. So mean of the process v of t is 0. So minus 48 into 0, then only I'll get 64. So 64 plus 36 is 100 watt. 36 plus 0 plus 64. So finally I'll get 100 watt as a answer. 100 watt is the answer. Okay. Next question. The autocorrelation function of the rectangular pulse of duration t. They given some signal x of t. X of t is a rectangular signal. Say, I can imagine like this. It is a rectangular signal with the duration t, with the duration t, capital T in the time domain. Now, what is the autocorrelation function of this rectangular function? So we should know the basic formula. what is ACF, basic formula. Please refer the basic. So expectation of x of t, then not expectation. And then directly we can write like this: x of t convolution with x of minus t. Okay, this is the autocorrelation function basic formula. X of t convolution with x of minus t. And another formula is also there, but this is one of the formula. So that means what? For a given signal, you have to find out what is x of minus t. Then again, you have to do the convolution operation. You have to do the convolution operation for this rectangular pulse. First, you should know what is x of t, then x of minus t. Then you do the convolution operation. So finally, you'll get the answer. Now, here you should also know what is the convolution. What is the convolution value? So once for a rectangular signal, if you do the convolution, that means both are having equal value. Okay, if both are having equal value means then you'll get the triangular pulse. You'll get the triangular pulse with the duration of 2t. So individually t, then totally it is 2t. So the answer is triangular pulse with the duration of 2t is the answer. Triangular pulse with the duration of 2t. Next, the power spectral density of the real process x of t for a positive frequency is given. Then what is the value of E of x square of t, then E of x of t? அதாவது x of t க்கு Fourier transform pair எழுதணும்னா sx of f இல்லனா sx of omega கிடைக்கும். The power spectral density means in the frequency domain. So instead of in the f domain, they were represented in the frequency domain. They were represented in the frequency domain. So now we want to calculate what is E of x square of t. What is E of x square of t? E of x square of t means power in the signal. E of x square of t means power in the signal. So now the power in the signal I can calculate from the power spectral density. E of x square of t is giving the power. So that power can be calculated from the power spectral density using this formula: integration minus infinity to plus infinite sx of omega d omega. As it is in the omega domain, I have to put 1 by 2 pi. Okay, if it is in frequency domain, here you should not put 2 pi in the denominator. Or if it is in the, as it is here in the omega domain, we are putting 1 by 2 pi. So now 1 by 2 pi integration 9 to 11, then the triangular function. Okay, the triangular function integration. Again, here it consists of triangular pulse, triangular function as well as the impulse, triangular as well as impulse. So for the triangular function, easily I can calculate the area. Easily, either I can apply integration or otherwise using area property, I can easily calculate what is the area, because integration means area. But for impulse, directly I cannot write. I have to apply the integration formula, and also you should note down whether that impulse is within your integral or not. If the impulse is outside of the integral, then definitely integration value is 0, but the impulse is present within your integral. Okay, whether it is within or outside, they will clearly mention. See here, this is the definition of impulse, where omega is equal to 10 power 4, that means 10k. 10k is the answer. Again, you can observe here, 10k. So this is indicating 10k, this is 9k, this is 11k, because scale is in the k, 10 power 3. So definitely this impulse is inside this integral. So what I will do, for impulse, I will apply the integration. For the impulse, I will apply the integration. You know, the integration of impulse is always 1. So this is omega minus 10 power 4. That means this is in between 9k and 11k. So definitely this impulse is present inside the integral. This is dw. Then what is the area of the triangular pulse? Or otherwise integration also you can apply. I am just applying the area 1 by 2. Okay, 1 by 2 of BH formula. 1 by 2, base is 1, then height is 6. 1 by 2, 1 into 6, and then 1 by 2, 1 into 6. Again, you should note down the frequency is in K. Okay, that means 1k and then 10k. So finally I will put that, okay, in terms of k. Then from this integration of impulse is 1. Okay, integration of impulse is 1. Again, already 400 is there. So 1 by 2 pi 400, 1 by 2 pi 400 plus, okay, 6 plus 6 is 12. 12 by 2 is 6. Already it is in the k scale. So 6k. 6k. So 6000 plus 400 is 6400 is 6400 divided by 2 pi divided by 2 pi. But instead of divided by 2 pi, we are getting pi. Mostly this may be the problem with the negative frequencies also, because whenever a spectrum is defined in the positive frequency, it has to be defined in the negative frequency also. So, okay, I will clarify this later. So now we are getting 6400 divided by 2 pi. But, instead of divided by 2 pi, they are putting pi. Okay, anyway, I will clarify this doubt in the later class. Okay, okay, I am getting this answer. The next, what they are asking, E of x of t. E means what? Average value. E means average value. E of x of t. E of x of t. Indirectly, E means average. Indirectly, it will indicate the DC component in the signal. Okay, DC component. Indirectly, it will indicate the DC component. Average value means DC component present in the signal. DC component, the effective DC component present in the signal only will become like an average. So here you can observe what is the presence of DC component. DC means generally DC means at zero frequency. At zero frequency, I am not having any value. At zero frequency, I am not having any value. So the average value of the random process is zero. Average value of the random process is 0. So option B is the answer. Option B is the answer. Next, consider a random process where amplitude is root 2 sine 2 pi t plus pi, where pi is uniformly distributed between 0 to 2 pi. Then what is the autocorrelation function? Already I have given you the standard formula. Whenever you have a cos omega t plus pi, then what is the autocorrelation function for this ACF? Autocorrelation function for this is a square by 2 cos omega tau. Here instead of a, they given root 2. So root 2 square by 2 is 1 cos omega. I have already told you tau means always time difference, t1 minus t2, or it may be t2 minus t1. So instead of tau, I have to put t1 minus t2. So finally the answer is cos of 2 pi t1 minus t2. Option D is the answer. For a random variable x is having following probability density function PDF, but the limit is going from -1 to +3, and then totally the range is 4, so definitely 1 by 4 will be in the y-axis. So now we have to calculate mean and variance. Mean and variance. Already standard formula is there. For uniform distribution, mean is b plus a by 2. Variance is b minus a whole square divided by 2. Okay, so what is the final answer? 3 b minus a, 3 plus 1, 4, so 2 is the mean. Then b minus a whole square, that means 4 square divided by 12, 16 divided by 12, 4 by 3. So answer is D. Answer is D. So what is the main observation here? The same distribution, if you put uniformly like this, -2 and then +2, then also you will get the same result, but mean may be different. Mean may be 0, but the variance will not vary. Variance actually indicating what is the difference, actual variation from the central value. So variance will not change, but mean may be changing. Okay. Next.
Sir.
Yes. Yes.
Sir, in previous problem answer is B. Mean is 1, sir.
Mean is sorry, B plus sorry, B plus A. Mean is 1. Yes, mean is 1. So அதாவது B plus A தானே கொடுத்துருக்காங்க. B plus A means 3 minus 1 is 2, 2 by 2 is 1. So answer is B only. Correctங்களா? B.
Yes, sir.
Yes. So next, 1 milliwatt video signal having bandwidth of 100 megahertz is transmitted to a receiver through a cable that has a 40 dB loss. Say this is the cable, it is having 40 dB loss. So whenever I transmit the signal, the loss that is present in the entire cable is 40 dB. And then they have also mentioned the effective one-sided power spectral density, that is 10 power minus 20 watt per hertz. Then what is the signal to noise ratio at the receiver? Here we have to calculate what is the signal to noise ratio. So they have clearly mentioned what is the power available with us, that is 1 milliwatt. And also they given what is the bandwidth of the signal. The bandwidth is 100 megahertz. If the power is 1 milliwatt, we have to write in terms of dB, because power means if you operate in terms of dB, then it will be simpler in general. And also answer is given in terms of dB. So I will convert this input power into in terms of dB. Then the power available with us is minus 30 dB. Okay, just apply the 10 log formula, minus 30 dB. Then already loss is there. So what is the power, signal power I will be receiving at the output? The signal power is equal to input power minus loss. Input power is minus 30 dB, and then minus loss is there already, that is minus 40 dB. So totally the power available at the output of the cable is minus 70 dB. Now I have to concentrate on the noise power. I am indicating N means N is the noise power. So noise power, you know that noise power is N0 into B. N0 they are given 10 power minus 20. Then bandwidth also they are given 100 megahertz. That means 10 power 8. So I will get 10 power minus 12. Then noise I will represent in terms of dB. Then I will get minus 120 dB. Now I know what is the signal power. I know what is the noise power. So we want to find out what is signal to noise ratio, or otherwise in terms of dB, signal power minus noise power. In ordinary number, we have to take the ratio. In terms of dB, we have to find out the difference. So what is the signal power? Minus 70. What is the noise power? Minus 120. Already minus is there. So 50 dB is the answer. So in this problem, noise with uniform power spectral density of N0 is passed through a filter having HW transfer function in frequency domain, that is 2 times exponential of minus j omega TD, followed by an ideal low pass filter of bandwidth B hertz. Then what will be the output noise power? See what they are telling. There is some noise with power spectral density N0. Okay, again the noise is having uniform power spectral density. Okay, noise is having uniform power spectral density, is passed through some system. That system is having response, magnitude response in the frequency domain, that is h of omega is equal to 2 times of e power minus j omega td. Then after that, it is passed through low pass filter, ideal low pass filter. Ideal low pass filter means it will allow all the frequencies below the cutoff range, corresponding cutoff range. Okay. So now, first of all, this noise is passed through this system. Okay, whether this may be the noise or signal, but it is passed through some system. Okay, yesterday I have given you one formula. Say this is the power spectral density of the noise at the input side, power spectral density of the noise at the input side, say Sn of F. Whether this may be the noise or signal, yesterday I given you one formula. What will be the noise power at the output of the system? So output noise power is equal to, please refer the formula, output noise power is equal to, what is the magnitude of the system, just to take the square, because system will be defined in terms of voltage. So we have to find out the, instead of voltage, we have to find out the power response. So just to take the square, then multiply the input noise power. Multiply the input noise power. So simply what will happen, this N0 will be multiplied by 4. So here I will get 4 N0. Again, this frequency is extending from minus infinity to plus infinite, or from 0 to infinite. Now what they are telling, so now N0 has become like 4 N0. Now also the bandwidth is infinite, but after that it is passed through low pass filter. Say the low pass filter is having bandwidth B. Again, low pass filter magnitude will be 1, because it is a ideal low pass filter. Ideal low pass filter will have magnitude of 1, then bandwidth they mentioned like B. Then this signal is passed through that filter. So definitely there will not be any magnitude change, but there will be the bandwidth restriction. Okay, because this filter will allow the frequency only up to B. So finally what I will get at the output of the low pass filter, after the low pass filter, I will be getting 4 times of N0, but up to the bandwidth of B, up to the bandwidth of B. So this is the output of the low pass filter. So what they are asking, at the output of the low pass filter, how much noise power will be there? So I know what is the shape at the output of the low pass filter. This is the spectrum shape. Then you just take the area, that is the power. So 4 N0B is the answer. This is the last problem. And I may not be last. Okay. 7th problem. An output of communication channel is a random variable V with the probability density function as shown in the figure. What is the mean square value? See, in general, you know the mean square value for standard function, say such as uniform distribution or otherwise normal distribution. Okay, for a standard function, already standard formulas are there. But here, this is the new function. Okay, so you should know the regular formula for mean square value. So what is the mean square value? E of x square. What is the mean square value formula? E of x square. E of x square means integration of x square f of x dx is the mean square value formula. So here instead of variable x, they given like v. So that means E of v square, then integration of v square. Then this is instead of f of x, they given f of v, then dv. Again, what is the range? So you have to go from 0 to 4. In general, the integral goes from minus infinity to plus infinity, but here the signal is defined from 0 to 4. So this is from 0 to 4. 0 to 4. Again, v square is there. Then what is f of v? Okay, f of v. What is the nature of f of v? So you have to write the equation for this one. You have to write the equation for this one. I think this has to be k. Say, I think this point is k. Then what is the equation of this one? Equation of this one, I hope y equal to mx plus c formula where c is 0. So slope is k by 4. So k by 4 v is the equation of this line, that is k by 4 v dv. Now you take the k by 4 outside, then 0 to 4 v cube dv, k by 4 again. I think we have to calculate k. Okay, I'll tell you how to calculate k. You know that whenever the probability is given, the integration of p of v from 0 to infinite or from minus infinite to plus infinite has to be 1. So as per that concept, what is the integration of p of v? That is k by 4 v dv is equal to 1. Again, this goes from 0 to 4, is 0 to 4. Or otherwise, a simple method also I can tell. Instead of going, you can do integration also, or otherwise just to try to calculate the area here. The area under this function has to be 1, because it is the probability density function. Any probability density function, area, overall area has to be 1. So what is the area here? 1 by 2, 4 times of k has to be 1. So k is equal to 1 by 2. K is equal to 1 by 2. Okay, we'll come here. So integration of v cube dv, then once if we do the integration for this one, you'll be getting v power 4 divided by 4. This is 4 and then 0. What is k? K is 1 by 2. Then 1 by 8, 4 power 4 divided by 4. That was the answer was done for. Are we getting any answer here? So 8 is coming. So 8 is the answer. Visible or the problem? Has anyone visible? Is it visible? Anyone? Cornerல வச்சிருக்க visible இருக்கா உங்களுடைய ஸ்கிரீன்ல?
Yes, sir.
Okay. Which of the following function can be a valid power spectral density of a real wide sense stationary process? Okay, so you should know the properties of power spectral density. Properties of the power spectral density. Okay, yesterday I told you the power spectral density is always even function. The power spectral density is always even function. That is the one property. And then power spectral density value can never be negative, because power cannot be negative at any point of time. So these are all the two properties. Okay, so here, anyway, at any point of time, we are getting positive values only, because there is no negative sign. Definitely all the functions are satisfying that second property. Okay, power is always negative. But whether all this function is satisfying this property, even function property, that you have to verify. First of all, we'll concentrate on the function c. What is the nature of this function? They are telling 25. 25 means constant 25. Then del of f minus 16. That means at exactly 16, we will have a impulse. So definitely this is not the even function. Even function means it must be symmetric with respect to y-axis. Even function means it must be symmetric with respect to y-axis. So it is not a even function. It is not a even function. Similarly, you try to apply, instead of f, you try to apply minus f. Definitely this is also not a even function. This is also not a even function. So only this one will satisfy the even function property. So they are having constant value of 10, and also they are having one impulse at y-axis, exactly at y-axis. So this diagram will satisfy the concept of even function. So option D only satisfying that power spectral density property. So D is the answer. Next, Consider the following statement regarding the autocorrelation function Rx of tau and choose the correct option. Just we should know the autocorrelation function properties. First one, Rx of tau, autocorrelation function is even function of tau. Yes, it is correct. Then they are telling autocorrelation origin is less than at any other point. Tau can be anything here. But this is not true. Okay, I already told you autocorrelation at origin is the maximum. Okay, at tau is equal to 0, you calculate something, that is the maximum value. At all other point, it has to be minimum. So it has to be in the reverse format. So this is wrong. Then third one, Rx of 0 instead of tau, if you put 0, that will give power of the signal if it is a power signal, or energy of the signal if it is energy signal. Here we have to make note. So in the last class, I told you Rx of 0 will always give power, but it will give energy also, because we do not know what is the nature of the signal. Whenever the signal is deterministic or random, maybe the X of t may be power signal, or it may be the energy signal. It may be the energy signal. So if it is a power signal, directly you will get the power. If it is an energy signal, directly you will get the energy. That is the another idea here. So far we are discussing only about the power, but if at all if the signal is energy signal, given signal X of t is the energy signal, then Rx of 0 will give directly the energy present in the signal. So option 1 and 3 is correct. Option 2 is incorrect. So here statement C is correct. So around ஒரு 10 ப்ராப்ளம்ஸ் வந்து நம்ம டிஸ்கஸ் பண்ணதுலேருந்து பார்த்துருக்கோம். ஆல்ரெடி நம்ம கவர் பண்ண டாபிக்ஸில் இருக்கிற ஃபார்முலாஸை பேஸ் பண்ணது. ஒரு சிலது லைட்டாக அதுலேருந்து டீவியேஷன் ஆகி கூட இருந்திருக்கலாம். ஸோ அதெல்லாம் வந்து பார்த்தோம். அடுத்தது நம்ம டிஜிட்டல் கம்யூனிகேஷன் வந்து பார்க்க போகிறோம். அதில் இந்த பிகினிங்கில் பிசிஎம் பல்ஸ் கோட் மாடுலேஷன் வந்து பார்க்க போகிறோம். இதில் ஏதாவது டவுட் இருக்கா இப்போ சால்வ் பண்ணதில்? எனிவன்? மூவ் பண்ணலாமா? அடுத்த டாபிக் போகலாமா? டிஜிட்டல் கம்யூனிகேஷனுக்கு. எனிவன்? ஓகே. ஸோ we have covered random process. ரேண்டம் ப்ராசஸில் இருக்கிற ப்ராப்ளம்ஸ், சம் ஆஃப் த ப்ராப்ளம்ஸ் அதையும் கவர் பண்ணியிருக்கோம். ஆல்ரெடி இந்த பிகினிங் இட் செல்ஃப் we have covered அனலாக் கம்யூனிகேஷன், அதனுடைய ப்ராப்ளம்ஸும் ஆல்ரெடி கவர் பண்ணியிருக்கோம். தென் in the last class we have discussed the information theory. So mostly in the next class we will cover MCQ type of problems in the based on the information theory in the next class. And today we will discuss about PCM, DPCM. If time is there, we will also see further modulation scheme, ASK, PSK, and then other modulation scheme. And later, after 1 or 2 classes, finally we'll be seeing fundamental of error correction, Hamming codes, and CRC. So now in this class we will start with the pulse code modulation. PCM, that is pulse code modulation. Pulse code modulation. ஓகே, இந்த நேம்ல பிசிஎம்ல பல்ஸ் கோட் மாடுலேஷன் அப்படின்னு ஒரு கொடுத்துருக்காங்க. இன் ஜெனரல் மாடுலேஷன் மீன்ஸ் we have to transmit a particular information to a longer distance. But here in case of PCM, we will not be sending our signal to a longer distance in PCM. So the main point you have to understand here, that is PCM is not a modulation technique. Okay, and the name maybe the கொடுத்திருந்தா கூட PCM is not a modulation technique. PCM alone I am telling. PCM மட்டும் வந்து அது ஒரு modulation technique இல்ல. PCM is not a modulation technique, that you have to understand first. Because whenever there is a modulation, we have to use carrier and all, but here we will not use any carrier. Then what is PCM? PCM is the representation technique. Okay, it is the representation of analog signal in digital domain. So it is the representation of is the representation of real-time analog signal. Real-time analog means signals will be varying continuously. It is a representation of real-time analog signal in digital domain as a digital data like ones and zeros. It is a representation of real-time analog signal in digital domain, because you should not get confused with the analog to digital converter. Okay, in the measurement and the instrumentation, we'll be studying analog to digital converter, or otherwise in the LIC subject, we may be studying analog to digital converter. There, at a time, we will be converting one analog signal into the corresponding digital value. Okay, that is the concept of analog to digital converter. But here, in case of PCM, continuously we will be converting the analog value into the corresponding digital value. So you should know the difference between the analog to digital converter and then PCM. Again, the PCM definitely it will involve the analog to digital converter also. Analog to ADC is the one part of PCM. Okay, ADC is the one part of PCM. Okay, so PCM is not a modulation technique. So it is the representation of real-time analog signal in the digital domain. Then, what are the basic component in the PCM system? Say we are at the transmitter side. Okay, again, it's not a modulation scheme. Still, we'll talk like a transmitter and then receiver. Okay, so at the transmitter side, what are all the components? So the first component is sampler. First component is sampler. So mainly here our idea is, our aim is, objective is to convert the real-time analog signal into the digital data, continuous stream of digital data. So the first one is the sampler. For the sampler, what is the input? Analog signal is the input, analog input. First, the analog input will be passed through a sampler, then quantizer, then quantizer. So sampler will do the discrete operation in the time domain. Quantizer will do the discrete operation in the amplitude domain. You know, analog signal time is also varying, amplitude is also varying, continuous nature. So அது வந்து நம்ம discrete மாத்தணும். So time discrete மாத்துறதுக்கு யூஸ் பண்றது sampler, amplitude discrete மாத்துறதுக்கு யூஸ் பண்றது quantizer. So first sampler, then quantizer. After quantizing, we have to assign a digital value. So that is encoder. That is encoder. Then output of this encoder is the digital data. Digital data, ones and zeros. Digital data. Again, directly you cannot send the digital data. Again, some coding scheme is there, line coding schemes. They use பண்ணி தான் வந்து send பண்ணனும். But at this moment, you just consider like it's like a ones and zeros. Then, whenever we have an analog signal, it will have some maximum frequency that I am mentioning like FM. It's not a single signal. Whatever FM I am mentioning is the maximum frequency in the signal. Maybe the frequency is spreading from 0 to FM. FM may be anything, 10 kilohertz or 1 kilohertz like that. But in reality, in general, for any general signal, directly we cannot tell this is the maximum frequency in the signal. Say, what I'm telling, say, for example, you take the voice signal. If you see in some books, they will give 0 to 5 kilohertz. In some other book, they will give 0 to 4 kilohertz. In other books, they will give 0 to 3.5 kilohertz. Okay, so there is no clear idea what is the maximum frequency available in the voice signal. But I already told you, most of the time we may be taking this one 0 to 4 kilohertz. That means what? Almost 90% of the 99% of the information will be available from in the spectrum 0 to 4 kilohertz. Remaining 1% of the signal may be available beyond 4 kilohertz. So mostly we'll take 0 to 4 kilohertz. Again, to avoid that confusion, we have to fix what is that value. Okay. So that's why we should know very specifically what is this FM. So again, to fix this FM, what we will do, we will put one filter before sampler. Again, to avoid this confusion, okay, I must be very clear. Okay, what will be the maximum frequency that is available before the sampler? Then only I can apply the sampling theorem. You might have studied sampling theorem. Sampling theorem is Fs greater than or equal to 2Fm, sampling frequency. Okay, quickly I'll come back what is the sampling frequency. But here, first of all, you have to fix Fm. Okay, so to fix Fm, here I will be using one low pass filter. So what I am telling, before sampler, there must be one device. The device is low pass filter. The low pass filter output only will be given to sampler. So what is the job of this low pass filter? So some analog signal is coming. So this low pass filter will fix Fm. It will fix Fm. So it will fix Fm. What is the maximum frequency available in the signal that I am fixing? Okay, you have to fix, because based on that you have to put the sampler. So to fix that Fm, I have to put the low pass filter, or otherwise if you are not using low pass filter, you do not know what is Fm, automatically you will be violating this formula. Once if you violate this formula, okay, so that will create a problem at the receiver side. Okay, that I'll tell you later what is that problem. Okay, so mostly distortions will be there. Okay, see, already we are having 1% loss of information. No problem. Once if you follow this procedure, definitely 1% loss of information will be there. But if you do not use low pass filter, what will happen? More than 5% of the information will be lost at the receiver side if you do not use low pass filter. So it is always better to use low pass filter. Okay, you must have a control over that to avoid the distortion at the receiver side. The distortion is called aliasing. The distortion here, it is called aliasing. So if you follow this procedure, we will not have any distortion or aliasing. So that's why this filter is also called as anti-aliasing filter. This filter is also called as anti-aliasing filter. This is the example கேட்பாங்க. Why we are using low pass filter before sampler? To avoid aliasing. That's why the name is anti-aliasing filter. Okay, somehow we have fixed what is Fm. So here I have to put one low pass filter. Once if I put low pass filter, I should know very clearly what is Fm. Before that, I do not know what is Fm. Now I am fixing Fm. The moment you fix Fm, again Fs you have to fix sampling frequency. What is sampling frequency? Say I am having some analog signal. It is varying in time. Or otherwise, for simplicity, I will take it as a sinusoidal signal for analysis purpose. Some signal, I am taking some signal, analog signal. Now I want to convert this analog signal into the corresponding digital signal. First of all, I should pick up the sample values. So these are all called the sample values. I have to fix the time. So at what time I am taking the sample, I have to. So now this will have some time. Okay, say for example, I am between 0 to 1 second. Then how much sample you are taking within 1 second? Okay, see, you can take any number of sample. In 1 second, say once the signal is given, the signal will have some maximum frequency. Okay, anyway, you are in time domain. Now you can take samples. Okay, the sampling rate can be anything. Within 1 second, you can take 10K samples or 100K samples. Then what is the value? How much number of samples you have to take? So that's why they are giving one formula to avoid distortion at the receiver side. Definitely, what is our aim? Analog signal we are representing in terms of digital data. From the digital data, we have to recover back our original analog signal. That is the aim. Appo samples எடுக்கும் பொழுது, the sampling rate must be at least greater than 2 FM. Fs must be at least greater than 2 FM. Now, what is Fs? Fs is the sampling frequency. Okay, sampling frequency. Again, what is the unit of sampling frequency? It is not hertz. I may be mentioning like sampling frequency, but the unit is not hertz. It is like samples per second. So what is sampling frequency? Number of samples taken per second. Number of samples taken per second is called sampling frequency. See, the name may be sampling frequency, but what is the actual meaning? How many number of samples you are taking in 1 second? That is the sampling frequency. That is the sampling frequency. Okay, so Fs. So again, Fs they have mentioned, say for example, if Fm is 4 kilohertz, for voice signal, I am restricting my frequency maximum to the 4 kilohertz. That means Fs must be 8K. So what is the idea here? I have to take 8,000 samples per second. In 1 second, I have to take 8,000 samples, 8K samples. Okay, if you want to represent this information in terms of digital data, at least you have to take 8,000 samples, but it can be greater than that also. Suppose instead of 2 FM, you can use 3 FM also, but 2 FM is the minimum value. If FM is greater than 2 FM, say for example, instead of 8K, you can take 12K also, you can take 16K samples, it's your wish. But there will be some problem. Later. So first one understand try. So Fs means how many number of samples you are taking per second. Say for example, in some problem they are giving example. In a particular conversion technique, PCM technique, they have taken for 0.1 millisecond, okay, 500 samples have been taken. 500 samples taken. Then what is the sampling frequency? Okay, see, they have not mentioned for 1 millisecond. Sorry, 1 second. They are given for 0.1 millisecond, 500 samples have been taken. Then in 1 second, how many samples will be taken? So now, what is the sampling frequency? Anybody? Very simple. Sampling frequency means 500 samples have been taken for 0.1 millisecond. Then once if you do this operation, you will get 500K. So that means per second, 500K samples will be taken. Okay, 0.1 millisecond 500 எடுக்குறாங்கன்னா அப்போ 1 second 500 samples எடுத்திருப்பாங்க. அப்போ what is the sampling frequency on the case 500K. Okay, so 500K samples per second. Okay, again, what is the sampling interval? 1 second 500 samples irundaduna, what is the sampling interval? Simple, 1 by Fs. So 2 microsecond will be the sampling interval between the samples. Okay, 1 second 500K samples irukku. Between the samples, what is the time? Simple formula, Ts is equal to 1 by S. So 2 microsecond. This reverse panina 2 microsecond. If you have doubt, each sample will have 2 microsecond difference. You know how many number of samples are there? Okay, say 500K samples are there. Each sample is having the duration of sampling interval is 2 microsecond. If you multiply, you will get 1 second. If you multiply these two, you will get 1 second. That is the simple idea. So now, somewhat we understood what is Fs, Ts, and then everything. Then we'll come here. So now, we are defining Fs is equal to 8K, or in general, the minimum Fs, this I will call it as a minimum Fs, that is 8K, or there is another name for minimum Fs, that is the Nyquist rate. That is the Nyquist rate of sampling. Okay, F Nyquist, that is 2 times of Fm. F Nyquist rate. Nyquist rate of sampling means only 2 times of Fm. In general, it can be greater than 2 Fm also. So Nyquist rate of sampling. Now, in 1 second, 2 Fm samples are there. Then what is the sampling interval? Ts means sampling interval. Or otherwise, see, you can observe here. I have taken samples like this. Now, what is the time difference between these two samples? That is the Ts. Time difference between the two adjacent sample is called the Ts. Sampling interval Ts is equal to 1 by Fs, or it is 1 by Fs means 2 Fm. 1 by Fs means 1 by 2 Fm. So this is the sampling interval between the adjacent samples. இப்போ என்ன பண்ணோம், ஒரு அனலாக் சிக்னல் எடுத்தோம். ஒரு செகண்டுக்கு எத்தனை சாம்பிள்ஸ் எடுக்கணும்னு ஆல்ரெடி ரூல் இருக்கு, ஆர் அதர்வைஸ் நாட் 1 செகண்ட், இன் ஜெனரல் அதனுடைய மேக்ஸிமம் ஃப்ரீக்வன்சி என்னவோ அதுல இருந்து 2 டைம்ஸ் பண்ணணும். ஸோ தட் many நம்பர் ஆஃப் சாம்பிள்ஸ், அப்போ 1 செகண்டுக்கு 2fm நம்பர் ஆஃப் சாம்பிள்ஸ், அட்லீஸ்ட் 2fm நம்பர் ஆஃப் சாம்பிள்ஸ் வந்து எடுக்கணும். அதுக்கேற்ற போல நீங்க லைன்ஸ் போடணும். இப்போ டைம் டொமைன்ல டிஸ்கிரீட் பண்ணியாச்சு. அனலாக் டொமைனை நம்ம என்ன பண்ணணும், டிஸ்கிரீட் பண்ணணும். அனலாக் டொமைனை டிஸ்கிரீட் பண்ணணும்னா ஐ வில் புட் லைன்ஸ் லைக் திஸ். I will put like levels. This I will call it as a, in general, this is called as a levels. Again, how many number of levels you are assigning? 4 levels assign பண்ணலாம், 8 levels assign பண்ணலாம். Say in this case, I am just assigning 4 levels. So at any point of time, my sample value, either it will be, say, this is level 0, this is level 0, this is level 1, this is level 2, this is level 3. I am having 4 levels. At any point of time, my sample value will be mapped to the nearby level. Okay, either this will be mapped to this level, this sample will be mapped to this level, this will be mapped to this level. So somehow I am assigning each sample to the nearby level. Then what I will do, for each level, I will assign digital bits. Level 0 means 0, 0, level 1 means 0, 1, then 1, 0, then 1, 1. Okay, say for example, I am having this sample, so definitely this will be mapped to level 3. Then what is the corresponding data? Okay, this will produce 1, 1. Again, this sample is also will produce 1, 1. This also will produce 1, 1, 1, 1. Again, this is also 1, 1. But this is very close to level 2. Level 2 means 1, 0. Okay, again, if you come like this, say this will be mapped to level 1. Again 0, 1. So like this, you have to assign the bits. இப்போ என்ன பண்றோம், டைம் டொமைன்ல டிஸ்கிரீட் நேச்சரை கொண்டு வந்துட்டோம் யூசிங் சாம்பிளிங் ஃபார்முலா. அதுக்கப்புறம் ஆம்பிளிடியூட் டொமைன்லயும் டிஸ்கிரீட் கொண்டு வரணும். அதுக்கு லெவல்ஸ் அசைன் பண்றோம், நம்பர் ஆஃப் லெவல்ஸ். ஜென்ரலா அது வந்து 2 பவர்ல இருக்கும். 4 லெவல்ஸ் அசைன் பண்ணலாம், 8 லெவல்ஸ் அசைன் பண்ணலாம், 16 லெவல்ஸ், இது போல எத்தனை வேணாலும் அசைன் பண்ணலாம். பட் இஃப் யூ அசைன் 4 லெவல், ஈச் சாம்பிள் ஹேஸ் டு பி ரெப்ரசன்டட் பை 2 பிட்ஸ். ஏன்னா டிஜிட்டல்ல உங்களுக்கே தெரியும், 4 லெவல் இருந்தா ஒரு லெவலுக்கு மினிமம் 2 பிட்ஸ் அசைன் பண்ணி ஆகும். இதுவே நீங்க 8 லெவல்ஸ் அசைன் பண்ணிருந்தீங்கன்னா each sample will be assigned 3 bits. 16 levelsனா each sample will be assigned 4 bits. பட் என்ன ஐடியாங்கன்னா, இது நீங்க எத்தனை லெவல் ஒன்னாலும் அசைன் பண்ணலாம், அது ப்ராப்ளம் கிடையாது. பட் ஆனா அந்த பிட்ஸை வந்து அடுத்த சாம்பிள் வர்றதுக்குள்ள டிரான்ஸ்மிட் பண்ணணும். அதுதான் மெயின் ப்ராப்ளம் ஹியர். நீங்க ஒரு சாம்பிளை 2 பிட்ஸை வச்சு கூட ரெப்ரசென்ட் பண்ணலாம், 3 பிட்டோ 4 பிட் எவ்வளவு வேணாலும் பண்ணலாம். பட் நெக்ஸ்ட் சாம்பிள் வர்றதுக்குள்ள அதை டிரான்ஸ்மிட் பண்ணணும். ஏன்னா நெக்ஸ்ட் சாம்பிள் வந்து அதனுடைய ஓன் டேட்டா வரும், அதையும் நம்ம டிரான்ஸ்மிட் பண்ணி ஆகும். ஸோ இது எல்லாத்தையுமே வந்து நம்ம பார்க்கணும். ஸோ நவ் ஐ ஹவ் இன்ட்ரடியூஸ்ட் த லெவல்ஸ். ஓகே, லெவல்ஸ். ஸோ எல், ஐ ஹவ் இன்ட்ரடியூஸ்ட் எல். எல் இண்டிகேட்டிங் தி நம்பர் ஆஃப் லெவல். Number of level. So again, this comes under the topic of quantization. This process is called as quantization. So after sampling, we have to assign the level. Okay, that is called as a quantization. That is called as quantization. So L is indicating number of level. For each level, I will assign n number of bits. Okay, the bits, number of bits for each sample. Each sample, you can say each sample or each level. Number of bits for each sample, number of bits for each sample, or otherwise level, anything. Anyway, all the sample will be mapped to some level. So you can call it as for each sample or each level. Anything is okay. So now there is a relationship between L and N. If you carefully observe, number of level is equal to 2 power n. Number of level is equal to 2 power n. For simplicity, you see here, I am having 4 level. Again, for each level, I am assigning 2 bits. So definitely 2 power 2 is 4. So number of level is equal to always 2 power n, where n is the number of bits, L means number of levels, number of levels. Again, what will happen if you increase here itself? It is very evident. Suppose if you are trying to increase L, definitely n will increase. Or if you try to increase n, L will increase. அதுபோல L decrease பண்ணா n வந்து decrease ஆகும். So that is the main observation here. Say for example, I am trying to increase n, definitely L will increase. இல்லனா L increase பண்ணாலும் n வந்து increase ஆகும். இதனுடைய ப்ராப்ளம்னா என்னன்றது நம்ம லேட்டரா இதனுடைய some problem இருக்கு. இதெல்லாம் increase பண்ணாலோ decrease பண்ணாலோ there will be some problem. இதெல்லாம் அடுத்து நம்ம பார்ப்போம். Okay, so levels இதெல்லாம் வந்து அசைன் பண்ணியாச்சு. Now we'll define quantization noise. Okay, in the process of quantization, say, again, before that, we'll define one more parameter, step size. Okay, step size. Step size means what is the difference between the levels. Say I have assigned 4 levels, then what is the difference between each level? That is the step size. Difference in the levels is called step size. So the formula for step size is dynamic range of the signal. Dynamic range of the signal. Dynamic range means in the value. What is the minimum value? What is the maximum value in the analog signal? Dynamic range of the signal divided by number of level. Where what is the dynamic range? What is the maximum value present in the signal? Then what is the minimum value? Minimum value may be negative also. Here I have taken minimum value as 0 in this case. In reality, minimum value can be negative also. So in general, Vmax minus V minimum then divided by L. This is the step size. So now I'm going to define quantization error. I'm going to define quantization error, quantization noise. Quantization noise. Okay, for that, once again, I'll draw the diagram. Say I'm having some signal. I have assigned the level. Now I am here. When I am here, say this is level 0, level 1, level 2, level 3. Again, for simplicity, I will assume that this is 0 volt, 1 volt, 2 volt, and then this is 3 volt. Okay. So now this sample definitely it will be mapped to, see, in reality, this value may be 2.8 volt. But when you do the quantization process, this will be mapped to 3 volt. Definitely this will be mapped to level 3. Level 3 means 3 volt. Now we are at the transmitter side. Now when we go to the receiver side, can we recover back 2.8 volt from that 3 volt? That is the question mark. Can I recover back 2.8 volt exactly from the 3 volt? That is the question mark. So you cannot recover, because any voltage in between 2 to 3 or at least any voltage that is greater than 2.5 definitely will be mapped to 3. At the receiver side, we cannot demap exactly. Okay, so exact demapping is not possible. Okay, only we'll do some kind of approximation, but exact demapping is not possible. So that means voluntarily we are introducing some noise. So in the process of quantization, we are doing quantization. So here we are introducing noise. How much noise we are introducing? Around 0.2 volt is a noise. Okay, because 2.8 you are approximating to 3. Again, from 3 you can get exactly 2.8. That is a question mark. So you are introducing some noise. That noise is called quantization noise. That noise is called quantization noise. So this noise is not coming from anywhere else. The user we are introducing. Okay, we are in the process of converting analog signal into digital signal. We have to use quantization procedure. But once if you use quantization procedure, definitely some kind of noise will be introduced. That noise is called quantization noise. That is irrecoverable. You cannot recover back. You cannot remove that noise. Okay, so quantization noise not removable. You cannot remove it. Not removable. Once if it is introduced in the system, you cannot remove it. But you can try to decrease. You can try to reduce the quantization noise. Okay, we may by means of some other technique, say quantization noise, or otherwise I'll put like quantization error, noise or error. We may try to reduce. Okay, we may try to reduce by using some technique. We may reduce it. We may try to reduce it, but you cannot make it 0. We may try to reduce it, but once if it is introduced, it cannot be removed. Okay, in the system, once if the quantization noise is introduced, it cannot be removed. So that is the main point you have to note down. So in the exam, they will ask whether we can remove the quantization noise or not. So we cannot remove it. Once if it is introduced, it is irrecoverable. You cannot recover it back. Okay, so then what is exactly the quantization noise value? See, I have taken 2.8 volt. So now the quantization error is 0.2. Suppose if I am taking 2.5, this 2.5 may be mapped to 2 or 3 because both are at the equal distance. So definitely this will be mapped to 3 volt or it may be mapped to 4 volt. Or otherwise, suppose if I take 2.1, definitely this will be mapped to 2 volt because level 2 is the nearby. That time, what is the quantization error? Say that is 0.1 volt. In general, how to find out the quantization error? Say that is actual value and then quantized value. Actual value minus quantized value. So now my samples can be anywhere in between. Then if you carefully observe in this case, what is the quantization error, range of the quantization error range? If you carefully observe, the quantization error range can be from minus 5 volt to 0.5 volt. Okay, depending on at which value you are at any point of time, definitely the range will be within this only. ஏன்னா மிடில் போயிட்டீங்கனாலே 0.5 தான் டிஃபரன்ஸ் வரும். அப்போ ஆட்டோமேட்டிக்காக ஏதாவது ஒரு லெவலுக்கு போயிடுவீங்க. ஸோ இல்லை சப்போஸ் சாம்பிள் இங்கே இருக்குன்னா குவான்டைசேஷன் எரர் இருக்காது, ஜீரோவா இருக்கும். ஸோ குவான்டைசேஷன் எரர் ஜீரோவா வரலாம், பாசிட்டிவ் சைடு அப் டு 0.5 போகலாம், நெகட்டிவ் சைடு அப் டு minus 0.5 போகலாம். பட் மேக்னிடியூட் வைஸ் இஃப் யூ சி just to 0.5 volt. Okay, but if you follow this formula, this is from either from minus 0.5 volt to plus 0.5 volt. Okay, this is the range of the quantization error. Now, what is the maximum quantization error possible? What is the maximum? Here itself you can understand the maximum value in terms of value. I am telling the maximum quantization value is 0.5 volt. This is same as step size divided by 2. This is same as step size divided by 2. Step size we will call it as del divided by 2. Why step size del? What is step size? Yeah, you can easily understand. Step size means difference between the level. Now what is the difference between the level? That is 1 volt. So quantization, maximum quantization error is step size divided by 2. Del divided by 2 is the maximum quantization error. Okay. So step size na define manu. Step size na difference between the levels, that is del by 2. Again maximum quantization error வந்து possible another del கிடையாது, del by 2 தான் another maximum quantization error. And then one more observation we have to make that we will be using very quickly. What is the distribution of this error? See, what is the distribution? Whether see, I can get the error range, QE range. The error range is from minus 0.5. Minus 0.5 means I can get minus 0.4, minus 0.3, then 0, 0.1, 0.2, like that it goes. That means I can get any value of error. இப்போ இந்த எரர்ல ஏதாவது நம்ம கெஸ் பண்ண முடியுமா? ஜீரோ எரர் தான் அதிகமா வரும், இல்லைன்னா மைனஸ்ல இருக்கிற எரர் தான் அதிகமா வரும், இல்லைன்னா பிளஸ்ல இருக்கிற எரர் தான் அதிகமா வரும் அப்படின்னு ஏதாவது கெஸ் பண்ண முடியுமான்னு பார்க்கணும். ஏதாவது பயாசிங் இருக்கா இல்லையா, இல்லைன்னா யூனிஃபார்மா வர்றதுக்கு தான் சான்ஸ் இருக்கா? when we take many number of samples, say infinite number of samples, what is this distribution, whether this is uniform or non-uniform? So if you carefully observe, this is uniform. This will become like a uniform when you take many number of samples. What is the error occurrence distribution? That will be uniform. மைனஸ் தான் அதிகமா வரும்னு சொல்ல முடியாது, பிளஸ் தான் அதிகமா வரும்னு என்னால சொல்ல முடியாது, இல்லைன்னா ஜீரோ தான் வரும்னு சொல்ல முடியாது. ஏன்னா here itself you can observe, you are keep on changing the value. Definitely error also will be changing within the range. So again you cannot do any biasing here. So the error distribution is uniform. The quantization error distribution is uniform distribution. In the exam they will ask, what is the distribution of quantization error? That is in general uniform. So now almost we have defined all the formulas. Okay, then see, in the beginning we have taken Fs. Okay, Fs means number of samples per second. That means after applying sampling theorem, in 1 second I will be taking Fs, number of samples, then, and I also know how much bits is there in each sample, number of bits in each sample, then what is my data rate? See, ultimately, somehow I have assigned ones and zeros. Ultimately, I have assigned ones and zeros. Now, what is the data rate? What is the data rate that I will mention like RB? RB means finally, how many number of bits are there per second? How many number of bits are there per second? That is simply Fs multiplied with the n, number of sampling frequency multiplied with the n. What is the unit of this? Bits per second. What is the unit of this? Bits per second. Again, you apply the unit. See, this is number of samples per second, number of samples per second. This is number of bits per sample, number of bits per sample, sample cancel. So I will get bit per second is the unit. So finally, what is the digital data rate? That is n times of Fs, n times of Fs, RB data rate. Digital convert பண்ணிட்டோம். கன்வெர்ட் பண்ணிட்ட பிறகு அதனுடைய டேட்டா ரேட் என்ன அப்படின்னு கேட்டாங்கன்னா n டைம்ஸ் ஆஃப் எஃப்எஸ். எஃப்எஸ்னா சாம்பிளிங் ஃப்ரீக்வன்சி, என்னன்னா நம்பர் ஆஃப் பிட்ஸ் அசைன்டு டு ஈச் சாம்பிள். ஸோ நவ் ஐ வாண்ட் டு சென்ட் திஸ் டிஜிட்டல் டேட்டா டு தி ரிசீவர். Say we are in the baseband communication. Baseband means without any modulation, or mostly you can imagine like a computer communication. Now, say I am having some device. This is converting my analog signal into digital. Then now the output is digital. Say now this is connected to the computer. Now here we no need the complicated modulation and all. Directly it is connected with the wire. But this wire also has to support some bandwidth. Okay, now I know what is the data rate, digital data rate. Now what must be the bandwidth so that this will carry this digital data reliably over this wire? Okay, that is another question. So now I know what is the bandwidth. If somebody is asking what is the bandwidth needed to carry this digital data, that is the minimum bandwidth is RB by 2. Okay, please don't get confused with this. Okay, this is valid only at PCM. So in PCM, finally we are generating RB, that is n times of Fs. Then what is the minimum bandwidth needed? That is RB by 2. Again, this formula also will be modified a little bit. Instead of giving like this, sometime they will mention RB by 2 1 plus alpha, because again raised cosine filter is there, one concept there. Alpha will vary from 0 to 1. When you put alpha is equal to 0, that is RB by 2. When alpha is 1, bandwidth is RB. So that's why here I have mentioned bandwidth minimum. So this is possible only when alpha is equal to 0. Okay, if alpha is increasing, bandwidth also will increase. Okay, so at least please note down this formula. Again, there is the modified version of this formula, that is bandwidth is equal to 1 plus alpha divided by 2 TB, or in general write like 2 TS, or to avoid confusion you can write either TS or TB, but later on you have to understand what is the difference between TS and TB, or at least you write TB now. 1 plus alpha divided by 2 TB. This is the modified version. Okay. So now we know what is RB. RB is n into Fs. Then somehow we know bandwidth is related with the bit rate. So again, forget about this formula and all. Now what is the observation? If RB is increasing, definitely the bandwidth needed to carry that particular digital information also will increase. Bandwidth of the channel has to be increased. Bandwidth of the particular user. Okay, user, because user is giving the analog signal that is being converted into digital data. So definitely that will occupy the particular bandwidth, say user bandwidth. For that particular user, we need this much amount of bandwidth. So once if you increase the data rate, definitely bandwidth of the particular user will increase. Okay, bandwidth of the user has to be increased. And then you should also know the another concept in general. The bandwidth of the channel must be as high as possible. Bandwidth of the channel must be as high as possible. Then bandwidth of the user, okay, user bandwidth of the user must be as low as possible. Bandwidth of the user must be as low as possible. Why I am telling? See, channel bandwidth is the common bandwidth. Channel bandwidth is the common bandwidth. User bandwidth means and the particular user enna bandwidth use பண்றாங்க. So what is the advantage here? See, what is the relation? Then I can define n. N means bandwidth of the channel. Then, sorry, n means bandwidth of the channel divided by bandwidth of the user. See, anyway, channel bandwidth is fixed. We cannot change. Channel bandwidth is fixed. But if you try to reduce user bandwidth, you can accommodate more number of user. Okay, that is the main observation here. So what is the observation? In general, we are having some common channel. User is having their own bandwidth. But if the user bandwidth, by using some means, by some technique, if you are trying to reduce bandwidth of the individual user, you can accommodate more number of people. You can accommodate more number of people. Or otherwise, if you are increasing user bandwidth, you cannot accommodate many people. The number of user in the system will reduce automatically. So now we'll come to our discussion. In our discussion, RB is equal to n into Fs. When we increase L, say number of level, automatically n will increase. Automatically n will increase. Then if you increase number of bits or number of level, mostly we will be assigning more number of levels. Okay, more number of levels. Then the clarity of the signal, clarity will be better. Okay, when we take, when you increase n, automatically the clarity will be better. Or otherwise, you can observe this from the quantization error formula. The maximum quantization error we have defined like del by 2. What is del? Del means step size. Step size means V max minus V minimum divided by L. V minimum divided by L divided by 2, where what is L? L means 2 power n. L means 2 power n. So what you are observing here, when you increase n, automatically quantization error will reduce. Once quantization error reduces means clarity will increase. So when you increase number of level, or just from the common sense you can understand, just from the diagram you can understand, when you increase number of level, definitely error will reduce, that ambiguity will reduce, confusion will reduce, so clarity will increase. But what is another problem? Clarity may be better, but what is the another problem here? Okay, when you increase n, RB will increase. If RB increases, bandwidth of the user, particular user will increase. If bandwidth of the particular user increase, number of person that can be accommodated in the system will decrease. So what is the problem? If the bandwidth of the each user increases, number of people will get reduced. Number of person that can be accommodated in a particular system will get reduced. That is the major problem. Say, I will explain this with the real-time example. நம்ம இப்போ ஃபோனில் எல்லாமே பேசுகிறோம், நம்மளுடைய வாய்ஸ் தான் ஃபோனில் பேசுகிறோம் கால் பண்ணும்பொழுது. அதனுடைய மேக்ஸிமம் ஃப்ரீக்குவன்சி வந்து 4 கிலோஹெர்ட்ஸுக்கு ரெஸ்ட்ரிக்ட் பண்ணுறாங்க. அப்போ சாம்பிளிங் ஃப்ரீக்குவன்சி என்னவாக இருக்கணும்? 8K இருக்கணும். சம் நம்பர் ஆஃப் லெவல்ஸ் யூஸ் பண்ணுவாங்க. நம்மளுக்கு யூஸ் பண்ணுற லெவல்ஸ் வந்து 256. அதாவது நம்மளுடைய வாய்ஸை வந்து டிஜிட்டலாக கன்வெர்ட் பண்ணும்போது 256 லெவல்ஸ் அசைன் பண்ணி கன்வெர்ட் பண்ணுறாங்க. அப்போ நம்பர் ஆஃப் லெவல்ஸ் வந்து 256. தென் L is equal to 2 power n. From this, what is n? N is equal to 8. சரி, அப்போ what is the bit rate? Bit rate is n into Fs. n na 8, Fs na 8K. Then what is the digital data rate? 64 kbps. அப்போ நம்ம பேசுகிற வாய்ஸ் எல்லாமே ஜென்ரலாக ஃபோனில் வந்து என்ன பண்றாங்க 64 kbps கன்வெர்ட் பண்றாங்க. அதுக்கப்புறம் தான் அதை மாடுலேஷன் பண்ணி ஆண்டனா டவருக்கு சென்ட் பண்ணி மொபைல் டவருக்கு சென்ட் பண்ணி அதை ரிசீவருக்கு வந்து போகுது. இதுதான் வந்து ஜென்ரலாக நடக்குது எனி டிஜிட்டல் கம்யூனிகேஷன். ஈவன் கம்ப்யூட்டர்ல நீங்க பேசுறது கூட கம்ப்யூட்டர்ல ஸ்டோர் ஆகுதுன்னா டிஜிட்டலாக தான் ஸ்டோர் ஆகும். ஈவன் மொபைல்ல கூட எடுத்துங்க, நீங்க பேசுறது அனலாகா ஸ்டோர் ஆகாது, டிஜிட்டலாக தான் ஸ்டோர் ஆகும். பிகாஸ் எனி memory element cannot store the analog signal because analog signal will have infinite number of information. So with the finite amount of storage device, you cannot store infinite information. So in general, all the storage medium will store only the digital data. So இப்போ நம்மளுடைய வாய்ஸ் சிக்னல் இதெல்லாம் இப்படி தான் கன்வெர்ட் ஆகுது. சப்போஸ் இட் இஸ் ஹேவிங் சம் கிளாரிட்டி, நம்ம ஃபோனில் பேசும்போது இட் இஸ் ஆஃப் ஹேவிங் சம் கிளாரிட்டி. Suppose what will happen in another system, say 64 kbps tha. If another system instead of 8 kilohertz, if they are using 16 kilohertz, okay, then definitely what will be the RB? What will be the RB? Instead of 64 kbps, 128 kbps will be there for each user. Appo clarity will increase. So that means RB will increase, clarity also will increase, but what is the problem? You cannot accommodate more number of people. அதனால என்ன சொல்ல வரேன்னா, ஈவன் இந்த டெலிஃபோன் நெட்வொர்க் நம்மளுடைய வாய்ஸ் ஒரு சம் எக்ஸ்டெண்டுக்கு தான் ஆப்போசிட் சைடில் கேட்குது. அதனுடைய கிளாரிட்டி we can increase still further, but what is the problem? They cannot accommodate more number of user at a time. So you have to understand. Okay, so what will happen if I increase the clarity? You cannot accommodate more number of people. That is the major problem. So again, there must be some common value. So that's why they have mentioned this. There should be some optimization between the clarity and then number of user at a time. So based on that, they have fixed this value practically. Okay, so அப்போ clarity ஒரு வகையில இன்க்ரீஸ் பண்ணா என்ன ப்ராப்ளம் வருதுன்னு பார்த்தோம். more number of peoples நம்ம வந்து என்ன பண்ண முடியாது, accommodate பண்ண முடியாது. That is the major problem in the PCM system, pulse code modulation system. Now we will find out the quantization, signal to quantization noise ratio. Okay, signal to quantization noise ratio. Fine. Signal to, generally நம்ம signal to noise ratio ன்னு சொல்லுவோம். Here noise is due to the process of quantization. So that's why this is signal to quantization noise ratio, SQNR. இப்போ இதுக்கு நம்ம ஒரு practical values எதனா எடுத்தாகணும். signal, say I am having some signal x of t is am sin omega t or cos omega t. Am sin omega t is the analog signal that I want to convert the signal into digital data. So I want to find out signal power as well as the noise power. You know what is the signal power of this signal? That is simply am square divided by 2. This is the signal power, common formula. Then I want to find out what is the noise formula, noise power. You do not know what is the nature of the noise, but you know one thing, noise distribution. You know noise distribution. Say the quantization error can vary from minus del by 2 to plus del by 2. Already we have identified this. What is the minimum quantization error? Minus del by 2, அதாவது magnitude wise del by 2. The range is from minus del by 2 to plus del by 2. That will have uniform distribution. Then once if it is uniform, what is the y-axis value? That is 1 by del. So this is the distribution, probability density distribution for quantization error. So FQE, then QE, probability PDF. So the quantization noise nature I have given in terms of PDF, probability density function. Then I have to find out what is the power of this distribution. Already I know to calculate the power, I will be using this formula, E of x square formula. But here, instead of x square, I am having QE, quantization error square formula. So now I want to apply this formula. What is E of QE square? So that is integration. Again, limit goes from minus del by 2 to plus del by 2. Then x square into f of x. So this is f of QE. Then instead of dx, I will have dQE. Now I know what is the distribution value. That is 1 by del. So here no x here. You will not get any x. Now I know what is the f of q. That is 1 by del. That is 1 by del. So I'll substitute that value. Minus del by 2 to plus del by 2 q square. This is 1 by del, then dq. So now q square 1 by del you can take out, because this integration is with respect to q. Then if you do the integration, q is cube divided by 3, then apply the limit del by 2 minus del by 2. Once if you solve this, just instead of q you apply del by 2. That's it. Finally you will get del square by 12. Okay, again with the help of simple formula we can write. We know for uniform distribution what is the formula? BA square divided by 12. In our case, what is B? Del by 2. What is A? Minus del by 2. So this is plus del by 2 divided by 12 whole square. So that is del square by 12. So this is quantization noise power. Okay, so now I have derived quantization noise power. That is del square divided by 12. Already I know what is the signal power. Then I and also know the quantization power, quantization noise power, that is del square divided by 12. Now I want to calculate the ratio between these two. Before that, we'll calculate what is del, step size. So step size del I have defined like dynamic range, that is V max minus V minimum divided by 2. V max minus V minimum divided by 2. For the given signal, sinusoidal signal, what is the maximum value? AM. AM is the maximum value, minus of minimum value is the minus AM divided by, it is not 2, that is number of level. Okay, that is number of level. Again, number of level is 2 power n. So this is 2 times of AM divided by 2 power n. Okay. So now I have represented del in terms of the actual value, in terms of maximum amplitude and the number of bits. Now I'll try to find out signal to quantization noise ratio. That means signal power divided by noise power. Already I have calculated the signal power, that is AM square divided by 2. Now noise power is del square divided by 12. Del I have already calculated. This is del. So 2 times of AM divided by 2 power n whole square divided by 12. So now if you solve this carefully, a very simple mathematics, if you solve this, finally you will get 3 by 2, 2 power of 2 power n, or may not be, it's like this, 2 to the power of 2 power n. 3 by 2, 2 to the power of 2 power n. Now the question here is, okay, see, ultimately I got some answer, signal to quantization noise ratio. Just you apply this formula, or otherwise, can I try? Say, I'll try. Yeah. So this is AM square divided by 2. This 12 will go up. This 12 will go up. Then 4 times of AM square. Then 2 power n. 2 power n whole square. 2 power n whole square. 2 power n whole square. So AM square cancel. 2 means 6. 2, 3 by 2. This 2 power n whole square will go upwards. So 3 by 2. 2 power n whole power 2. 2 power n whole power 2. So now, what is the 3 by 2? 3 by 2. Can I write this as 2 to the power of, can I interchange this 2 and n? 2 to the power of 2 power n. In some book, they might have given like this, 2 to the power of 2 power n, 2 to the power of 2 power n. So once if you take the logarithmic value, once if you represented this in terms of dB, signal to quantization noise ratio in terms of dB, then the final answer here is 1.86n, 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 then dB. 10 log formula apply பண்ணணும் இங்க இருக்கிற நம்பருக்கு n எதுவும் பண்ண முடியாது, so அது வந்து 6n ன்னு வரும். Then again I can write the modified version of this. Say this is 3 by 2. I can a power m whole power n formula 2 to the power of 2n also 2 to the power of 2n. Please verify this. All are correct or wrong. You take some number for n, some random number, different number. Just verify it. All the expressions are correct or not. Okay, if it is correct, then SQNR in dB, I can write like this 1.8 plus 6n dB. Now, what is the observation here? I know when I increase n, clarity will increase. That means when I increase n, here itself, it is indicating SQNR is increasing. Signal to noise ratio. ஏற்கனவே சொல்லியிருக்கேன், signal to noise ratio increase ஆச்சுன்னா நம்மளுடைய communication வந்து better-ஆ இருக்கும். Why it is increasing? Because I know when n is increasing, definitely quantization noise will reduce. So once quantization noise reduces means definitely signal to quantization noise ratio will increase. அதுதான் வந்து நம்ம final expressionலயே அதான் பார்க்கிறோம். இப்படி increase ஆகுது. Now what is observation? Suppose if I am increasing n by 1 bit, then SQNR will increase by 6 dB in terms of dB. See, when I put n is equal to 1, this is 6 dB plus 1.8. If it is 2, 12 dB. So for every 1 bit increase, the signal to quantization noise ratio increases by 6 dB, or otherwise in terms of number, it increases by 4 times. 4 times. Here you can observe. When you put n is equal to 1, this will give 4. When you give n is equal to 2, this will give 16. Anyway, this is constant. 16. That means for every 1 bit increase, in terms of number, it increased by 4 times. In terms of dB, it increased by 6 dB. Or otherwise, if you have doubt, you take 10 log of 4, that will give 6 dB. Okay, so either it increases by 4 times or it increases by 6 dB. That is the important observation from here. Important observations from here. So that வந்து நம்ம இன்னைக்கு ஸ்டாப் பண்ணுவோம். We started with the PCM pulse code. Sorry, startingல நம்ம problem solve பண்ணோம். Then we started with PCM pulse code modulation. அதுல different block இதெல்லாம் வந்து பார்த்தோம். Sampler, quantizer, then encoder. Encoder means assigning level to bit assignment. Encoding means level to bits assignment. ஒவ்வொரு லெவலுக்கும் bits assign பண்றது தான் வந்து encoder. Then basics இதெல்லாம் பார்த்தோம். How to fix FS, minimum FS என்னவா இருக்கணும். Then what is the relation between FS and TS இதெல்லாம் பார்த்தோம். Then next we have defined step size. Okay, step size depends on the number of level and then dynamic range. Then we have seen the quantization error. Maximum என்ன quantization வர chance இருக்கு. Okay, the maximum quantization error is related to the step size. That means del divided by 2. Then what is the overall bit rate? That is RB is equal to n times of FS. Then we have seen the units relation. Then to transmit this signal over a particular channel, we need some bandwidth, that is half of the bit rate. In some other time, if you use raised cosine filter concept, we have to use this formula where alpha will vary from 0 to 1. So bandwidth, we can also write like 1 plus alpha divided by 2 TB. அதுக்கப்புறம் சேனல் பேண்ட்வித்துக்கும் யூசர் பேண்ட்வித்துக்கும் என்ன ரிலேஷன் பார்த்தோம். When we increase RB, user bandwidth will increase so that you cannot accommodate more number of user. That is the major problem. But once if you increase RB means either you may be increasing N or FS. That means indirectly you will be increasing the clarity. Okay, clarity. You are increasing clarity means quantization error will be decreasing. Quantization error will be decreasing, but you cannot accommodate more number of people. அதுக்கு ஒரு எக்ஸாம்பிள் ரியல் டைம் எக்ஸாம்பிள் சொன்னேன். Then signal to quantization noise ratio என்னன்றதை கண்டுபிடிக்கணும். I have taken usual signal, ordinary signal, sine signal. For that, this is the power. Then noise means here quantization noise. I know the nature of the quantization noise, that is uniform, and also it goes from minus del by 2 plus del by 2. Then using the formula from the random process, I can calculate the power of the quantization error, quantization noise power, that is del square by 2. Either you can do the derivation or you can remember the uniform distribution formula. From that also you can calculate del square by 12. Then del I am representing in terms of amplitude, and then number of steps, number of bits. Then once if you do the mathematical adjustment, finally you will be getting expression like this, different expression, all are same. Then finally I'm writing this SQNR in terms of dB, so 1.8 plus 6n. So for every 1 bit increase, the signal to quantization noise ratio will increase because noise will decrease. That means quantization noise will decrease. So finally for every 1 bit increase, SQNR increases by 6 dB, or it is in terms of number. If you are representing in terms of number, it will increase by 4 times. This is the final observation. Again, at the receiver side, say finally we have converted in terms of bits. Somehow we have converted in terms of bits. Mostly in our example, each sample we have assigned into 2 bits. Each sample we have assigned into 2 bits. Now based on this bits, okay, I have to form the levels. Say I will get diagram like this with help of the level. Now we are at the receiver side. So first I have to decode this. Okay, from the bits at the receiver side, I have to form the digital diagram, digital signal. So now I will get in terms of levels. Then from the levels, I have to get the exact shape. So first of all, after receiving the bits, you have to decode it. Then you have to pass it through a dequantizer. So decoding means assigning levels. After assigning levels, okay, that has to be converted into the diagram. So that will be done with help of the dequantizer. Then finally, from this step diagram, we have to get the actual original signal. So here we will be using low pass filter. Okay, at this point this may not be very evident how we are getting exact output from this step diagram with help of the low pass filter. In future, if time is there, I will explain this. So at the receiver side, we are using decoding. This is the receiver side. At the receiver side, we are using decoding, then dequantization, then low pass filter. At the output of the low pass filter will be the analog signal, original analog signal. Here, this low pass filter will do the smoothing operation. That means here the diagram will be something like this with help of the steps. So that discontinuities will be removed by low pass filter. You know the properties of low pass filter. It will allow only low frequency, but at the place of discontinuities, it will produce very high frequencies. Maybe you might have studied in the signal system. So automatically that high frequencies will be removed by low pass filter. Then finally you'll get the smooth output. That will be the original analog signal. So இன்னைக்கு இதோட ஸ்டாப் பண்ணுவோம். In the next class we will continue with this next version, that is DPCM, delta modulation, then later on digital communication.